Hello, Algebra 2. This is the last section of Chapter 5. It's called the Rational Zero Theorem. So this is just another tool that we're going to have for when we need to graph and find the zeros of polynomial functions. So if you think back, we've talked about the factor and the remainder theorems. And we've talked about solving by factoring. We've talked about solving by several different ways. We've talked about graphing. We've talked about end behavior. And this is just another way to be able to find out some possible zeros of polynomial functions. So notice we're going to identify possible rational zeros, and then we're going to find all of the rational zeros. Remember that rational numbers, they are not imaginary numbers, they're real numbers that can be written as fractions. So they include fractions and integers. All right, so usually it's not practical if we're just trying to figure out the zeros of a polynomial function by hand. It's not practical to test all possible zeros. So we're not going to try 1, 2, 3, 4, 5 forever. And also, if the zeros are irrational, that's really hard to try. How do you test the square root of 2 or the square root of 3? So the rational zero theorem helps narrow down the possibilities of possible zeros that we can test. So this is the rational zero theorem. It says that if p of x is a polynomial function with integral or integer coefficients, then every rational zero of my equation set equal to 0 is of the form p over q, which is a rational number in simplest form, where p is a factor of the constant term. This is important. P is a factor of the constant term, and q is a factor of the leading coefficient. So I'm going to take all of the factors of the constant term over all of the factors of the leading coefficient to get possible rational zeros. So for example, in this polynomial f of x, p is negative 40 and q is 6. So for example, 4/3, if 4/3 is a possible zero, then 4 would have to be a factor of 40, which it is, and 3 would have to be a factor of 6, which it is. Again, these are possible rational zeros. We would have to test 4/3 to see if it's actually a zero of the function. And then we have this corollary, and if you'll notice up here, the corollary applies only if the leading coefficient is 1. The corollary says if p of x is a polynomial function with integral or integer coefficients and a leading coefficient of 1 and a non-zero constant term, then any rational zeros of p of x must be factors of the constant term. This makes sense because it's still p over q, but in this case q, which is the leading coefficient, is 1. So any fraction over 1 is just going to be the same as p. So you would just have to find the factors of the constant term in that case. So let's look at what this would look like. This says list all of the possible rational zeros of f of x equals 3x to the 4th minus x cubed plus 4. So remember, rational zeros have the form p over q, where p is the factors of the constant term, which in this case is 4, and q are the factors of the leading coefficient, which in this case is 3. So what I usually like to do is make a list of the factors first and then arrange them as the fractions. So what are the factors of 4? 1, 2, and 4, right? But we have to take into account positives and negatives. This is pretty easy. You just have to put a plus or minus in front of each factor, because negative 4 is a factor of positive 4, and positive 4 is a factor. Positive and negative 2 are both factors, and positive and negative 1 are both factors. Then we're going to list our factors of q, the leading coefficient, which is 3. Well, the factors of 3 are just 1 and 3, but again, I have to take positive and negative factors into account, so I just put a plus or minus in front of each one. So this is pretty straightforward. Now we're going to arrange my rational zeros of p over q. You have to be a little bit strategic when you do this so that you don't miss one. So I usually start with one of my factors of p and I arrange it over all of my factors of q. So in this case, I have 1 over 1. Well, 1 over 1 is just 1. So my possible rational zero will be plus or minus 1. Then I have to do my plus or minus 1 over 3. So I have to do 1 over 1 and 1 over 3. So that 1 over 3, we just leave it as a fraction, plus or minus 1/3. Now I'm going to do the same thing, but with my 2. So I'm going to do 2 over 1 and 2 over 3. 2 over 1 is 2, so plus or minus 2, and 2 over 3 is 2/3, plus or minus 2/3. Then I'm going to do the same thing again with 4. So 4 over 1, whoops, didn't mean to erase that, plus or minus 4. So 4 over 1 and 4 over 3. 4 over 1 is just 4, so plus or minus 4. And 4 over 3, leave it as a fraction, 4/3. So this is the list of possible rational zeros. Not all of these can be zeros, because according to the fundamental theorem of algebra, I can only have 4 roots, right? And here we obviously have a lot more. We have 2, 4, 6, 8, 10. We have 12 possible rational zeros. What this does is narrow down the choices if we're going to try to find out what rational zeros this function has. It narrows down the choices. So here, I wouldn't try 3, because 3 isn't in this list. I would start with 1 and 2 and 4, and then move on to the fractions. All right, here we're going to do the same thing. In this case, my p is 15, or negative 15, and my q, in this case, is 1. So remember, the corollary says if q is 1, the only factors of 1 are plus or minus 1. That's not going to change any of the factors of p. So what are the factors of 15? Plus or minus 1, plus or minus 3, plus or minus 5, and plus or minus 15. So all of my possible rational zeros, p over q, since dividing by 1 does not change anything, it's just going to be the same as p, plus or minus 1, plus or minus 3, plus or minus 5, plus or minus 15. So this would be the list of the possible rational zeros of f of x. Okay, I want you guys to try this one. List all of the possible rational zeros. All right, your answer here should be C. And when you make your list here, here's your list of the factors of p, which is 6, and the factors of q. One thing I wanted to point out is notice that when I do 1 over 1, I get 1, right? So I get 1 and I get 1/2. But then when I do 2 over 2, I also get 1, right? 2 over 1 is 2, but then 2 over 2 is 1. I don't have to list it again. I already listed that one when I did 1 over 1, which is just 1, right? And so then I would do 2 over 2, which is 1. I already got that. 3 over 1, which is 3. 3 over 2, 3/2. 6 over 1 is 6. And then again, 6 over 2 is 3, but I already listed that one, so I don't have to list it again. Okay, try this one. All right, the answer here is B. Since my leading coefficient is 1, p over q is just going to be the same as p, because that 1 will not change anything. So my possible rational zeros are all of the factors, positive and negative, of 24. All right, so there's a difference between listing possible rational zeros and actually finding which one the rational zeros are. So once you've written out all of the possibilities, you start testing each one using synthetic substitution. Remember, with synthetic substitution, we do synthetic division, and if the remainder is 0, it means that our number is a 0 of the function. So let's see what we're going to do in this first example. So here we have a geometry example, so we're going to do a real-life application. We have this rectangular prism. Its volume is 1,120 cubic feet, and the width is 2 feet less than the height. So here's my height, we called it x. The width is 2 feet less than the height, so x minus 2, and the length, which is here, is 4 feet more than the height. So notice we have all of those in terms of x, so that we'll have a polynomial in one variable. So we're going to write the equation for volume. Volume is length times width times height. We know that our volume is 1,120 cubic units, and here's length times width times height. So I'm going to multiply those all out, and I get x cubed plus 2x squared minus 8x equals 1,120. Set it equal to 0 so that I can start solving. The leading coefficient is 1, so my possible rational zeros are factors of 1,120, which is pretty long. They listed them out for you, so you didn't have to list them all out. These are all of the possible factors of 1,120. That's a pretty long list to try, but at least it narrows it down from trying just any random number. If we do Descartes' rule of signs, coming back over here, we know that we have one sign change when I do p of x, right? When x is plugged in, I have one sign change. So that means that there's one positive real zero, right? And here, notice they didn't put the positives and negatives. Why? Because I'm doing a real life situation and the negative zeros would not make sense, right? So we're going to start testing. So here they're showing you what you would get when you plug in 1 with synthetic substitution. Your remainder is obviously not 0. When you plug in 2, you get a remainder that's not 0. But when you plug in 10, you get a remainder that is 0. So that means 10 is the real rational zero of this function. And that's pretty, you can stop there because we know there's only one real positive zero, I'm sorry. We don't have to take into account the negative zeros because we're talking about volume and about lengths of sides, and those can't be negative. So that means that x equals 10, and that means the other dimensions are 8 feet, because remember the width was 2 feet less than the height, and the length was 4 feet more than the height. So the dimensions are 10 feet by 14 feet by 8 feet. And when you multiply those all together, you do get the correct volume. All right, you guys try this one. All right, hopefully you got B. Here's the work for getting the correct function, and then you should have listed out all of the possible factors of 100. So they were a little bit nicer to you than they were in the last one. The factors of 100 are 1, 2, 4, 5, and so on. And then you start trying those factors with synthetic substitution. When you get to 5, you should get a remainder of 0, and that tells you, okay, that's going to be a positive real 0. And according to Descartes' rule of signs, notice there's only one sign change in my original polynomial, and so that means I'm only going to have one real positive 0. So after I find 5, I don't have to keep trying. Then you use the 5 to find the length, which is 10, and the width, which is 2. All right, here's our last example for this section, finding all of the zeros of this polynomial function. So this is all zeros. Positive, negative, rational, irrational, complex, all of that. So we are going to look, we know that we're going to have 4 because the degree is 4, and we're going to work through some of our other tools to see what else we can know. Well, f of x, how many sign changes do I have? Here I go from positive to negative, and from negative to positive. So if we make our chart, how many positive real zeros could I have? 2 or 0. Then if I were to do f of negative x, x to the 4th would still stay the same. X cubed would become negative. 19x squared would stay the same. That would become negative 11x plus 30. How many sign changes do I have here? 1, 2. So for negative real zeros, I can also have 2 or 0. And that means I'm going to need a couple more rows to my table like we did in previous sections. Then how many imaginary zeros could I have? Well, I can only have 4, so I can either have 2 positive, 2 negatives, and none imaginary. I could have 4 imaginaries or 2 imaginaries. So I can have no positive or negative real ones and 4 imaginaries, 2 negatives, 2 imaginaries, 2 positives, 2 imaginaries. And here our leading coefficient is 1, so when we use the rational zero theorem, we just need the factors of 30. Here they have them listed out for you with their positives and negatives. So we're going to start testing some possible rational zeros. Here they start testing with 1 and 2. You can really start with positives or negatives depending on what you want to do. Because there could be 2 positives or 2 negatives or none of either, but obviously we have to start with the real ones. So when you start doing synthetic substitution, here they're just doing it all in a table. When I plug in 2, I get a remainder of 0. So since f of 2 equals 0, I know x equals 2 is a 0, and my depressed polynomial, which we would get from here, would be 1x cubed plus 3x squared minus 13x minus 15. Based on our table at the beginning about Descartes' rule of signs, x equals 2 is a positive real 0, and I can only have 2 or 0 positive real zeros. So I need to look for another one. Here they show you that when you plug in 3, 3 is another 0. So my new depressed polynomial is now quadratic, And we can solve that the normal way by